Hello everyone and welcome back. So today I'll be talking about the L'Hopital's rule and I'll also present a short proof of one particular case of it. So L'Hopital is spelled this way, I believe. It's a French word. So this is L'Hopital's rule. Alright, so what really is it? L'Hopital's rule is an insanely convenient trick that helps you evaluate complicated limits which are of indeterminate forms. So when I say indeterminate forms, these forms include 0 by 0 when the limit is of the form 0 by 0, when it is of the form infinity by infinity, and when it is of the form infinity minus infinity. And I also believe there are three other forms, you can just look them up. So when the limit is of these six forms, what you can do is you can apply the L'Hopital's rule, which tells you that when a limit, say limit is x, it tends to c. So you have f of x is equal by g of x. When it satisfies any of these above six conditions, the limit is equal to f dash of c by g dash of c. So as you can already see, applying derivatives is a lot quicker than algebraically manipulating the limit in order to get a desired form. So this helps you save a lot of time. So to give you an example, let's have, say, limit of x tends to 1. So you have x cube minus 2x square plus 2x minus 1, the whole divided by x minus 1. Now if you'll notice closely, you can see that 1 is actually a factor of this thing over here. You can see 1 minus 2 plus 2 minus 1. So 1 will actually be a factor of this polynomial. So you can take x minus 1 out and then you could cut both x minus 1 from both the numerator and denominator, and then you have to do long division to find the other polynomial that you will get from dividing this, and then you have to evaluate that. So it's a really long process if you don't know what the L'Hopital's rule is. But since this is of the form 0 by 0 when you try and evaluate the limit, what you can do is you can take the derivative of the numerator and the denominator. So this limit is nothing but 3 into 1 square, that is 3x square. So I'll substitute the value of x here, minus 4 into 1 plus 2. Alright, and so denominator is just derivative of x is 1 and 1 is a constant, so it just vanishes. So you have let me just check if it's correct. Yeah, I think it's correct. So you have 3 minus 4 plus 2, so it's 1. So all I did was take the derivative of the numerator and denominator, and I got this answer. And when I actually do it in my head, it'll be much quicker, maybe just 5-10 seconds at max. There's that. I don't think I need to elaborate any further on how massively convenient this rule is, but why does it actually work? And sadly enough, I didn't think to ask this question first when I was actually taught this rule, and thus when I kept applying this rule wherever I had limits, I felt vaguely uncomfortable, thinking, why does it even work? So here, after having seen the proof, I feel a lot more comfortable. So I hope that after seeing the proof that I showed to you guys, you too will feel much more comfortable applying this rule. So, but before that, let's actually look at how we define the derivative, because that's crucial to actually seeing how the proof works. So the derivative in terms of limits is simply defined as the limit as the variable x tends to some constant a. So we have a function f. So we have function f of x minus f of a. That's the value at which the derivative is being evaluated, the value of x at which it's being evaluated by x minus a. Of course, there's also the graphical interpretation, but algebraically speaking, this is how the derivative is defined. So I don't think I need to elaborate any further on this. I mean, this is what the calculus is really based upon. So using this definition of the derivative, let us try and see if we can get this rule over here, which is the L'Hopital's rule. Okay, so let's take that limit over there. We have limit of as x tends to c of, oh wait, c is added, right? C f of x by g of x. Remember, I'll be proving this for a special case in which it's of the form 0 by 0. So what I'm assuming over here is f of c, that is the limit that we are evaluating, the value of x at which the limit is being evaluated, is equal to g of c is equal to 0. Right? So we can write this whole thing as f of x minus 0 by g of x. It really doesn't change anything, and of course there's a limit. Alright, so then we can replace this with limit as x tends to c of f of x minus f of c by g of x minus g of c. Alright, and then what we do is, it's a really neat trick, we divide both the numerator and denominator by x minus c. So when we do that, you'll see just exactly what we get. So f of x minus f of c by x minus c, and since we can evaluate the limits in the numerator and the denominator separately, that's what I'll do over here. So I'll write this as another limit as x tends to c, g of x minus g of c is by x minus c. And now if you've been paying close attention, you know what this means. So this is nothing but f dash of c by g dash of c. And that is what we set out to prove. So it's a really simple proof, nothing extraordinary. But what it really does is that it helps cement that intuition behind actually using the L'Hopital's rule. So I believe this is a pretty short video, much shorter than my other videos, but I think that it was necessary to make because this is actually a pretty interesting part in calculus, and it's also very convenient, so I thought that you guys should feel good about using this rule if that makes any sense. So with that, I thank you for having watched this video. Bye.